All right, here we go again. Now we're talking about particle motion problems. Particle motion, exciting. Let's see. Particle motion. Well, let's go through this together really quickly. Particle motion problems deal with particles that are moving along the x or the y axis, meaning horizontal motion, vertical motion, horizontal, vertical. Things that might do that, like a vertical, be like a yo-yo, right? Like a yo-yo going up and down. Horizontal, you can think of like a car on a road. It's going horizontally, just in one direction. So look at that. So we're speaking about horizontal and vertical movement. I'm so excited. Okay. We're talking about position, velocity, and acceleration of a particle's motion. Okay, and we can do some defining of these functions, but the particle does not move along the graph of a function. That's really important to try to understand. It moves along the axes, x and y. Okay, oh, look at that. It moves along an axis. Okay. Usually we're talking about the x-axis. We're going to come back and revisit this soon when we come back after the break and finish off all of our curriculum in Unit 6 and 7. Then we'll deal with vertical motion. But for now, we are sticking with horizontal motion, meaning left and right only, not up and down, left and right. So now we're going to start talking about velocity and acceleration in terms of position. So let's see. Average and instantaneous velocity. So let's see. Suppose P of t is a function which defines the position of a moving object at a time, let's call that time t. Then the average velocity is equal to the average rate of change of position, which is just p of a minus p of b. P is the position function over a minus b. And the instantaneous, did I spell that right? Now it's sort of spelled right. The instantaneous velocity is equal to p prime of a at some point a. Okay, so a particle's position is given by the function p of t equals e to the t times sine t. P of t is measured in centimeters and t is measured in seconds. We're going to answer the following questions. So the first question is, what is the average velocity on the interval from t equals 1 to t equals 3 seconds? And we need to indicate appropriate units of measure. So we're trying to find the average velocity. I'm just going to say velocity average is equal to p of 1, p of 3, 1 minus 3. This, of course, would go into the calculator. I'd plug this into my y1. And you can choose to find your average velocity however you see fit. We'll get 0.274, thinking about units, centimeters per second. Centimeters per second. Average velocity. Next question is instantaneous velocity at t equals 1.5. Same thing, include units of measure. So I suppose you could actually just go right to the calculator for this, and you know how to do math 8 and get the derivative of this function at a particular value. Or you could find the derivative if you wanted to, just for a little extra practice. P prime of t is going to require product rule. So first times the derivative of the second plus second times the derivative of the first. And then however you want to find p prime of 1.5, you're going to get 4.787 centimeters per second. So the instantaneous velocity is a bit faster, or significantly faster than the average velocity. Okay, let's see, what else? I just want to make kind of a random note before I forget it, because I know it comes up in the classwork questions, and so if I don't revisit it later, at least you see it here. I just want to make a note that speed is equal to the absolute value of velocity, meaning that the speed is always positive, velocity has direction, speed does not. So just to kind of think about that, if we're talking about horizontal motion, that's what we're focusing on now, only horizontal, left and right, not up and down, just horizontal. If the velocity of some function is greater than 0, it's positive. That means we're moving to the right. And if the velocity is less than 0, that means the particle, the object, the whatever, is moving to the left. Okay, next page. Let's try to make a couple of connections now. So when given a function, f of x, thinking about how we found the slope of the secant line on some interval from a to b. We've done this a lot, right? So we found that the slope of the secant is equal to, just using what they gave us, f of a and a minus b. This gives us the average velocity. Then, in terms of position of a particle, what does the slope of the secant line correspond? Oh, we already said that. I'm answering things out of order. Sorry, guys. So the slope of the secant line corresponds to the average velocity. And now we're going to think about instantaneous velocity. Instantaneous is slope of the tangent line. This is not the first time we've ever said this. We've said this a ton. And that would be f prime at some particular point. And that corresponds to instantaneous, spelled it right on the first try this time, velocity. Okay, so average and instantaneous now. Acceleration. We have not used the word acceleration at all in class before, I do not think. So let's do some defining right now. So if p of t, or sometimes you see s of t, p of t, and s of t a lot for position function, is position, and p prime of t is always going to be equal to velocity, v of t, the velocity, then we've got two things. Average acceleration, average, thinking about using average rate of change, slope formula, would use the velocity function to estimate it. So this is equal to v of a minus v of b and a minus b. And we could say also that the instantaneous acceleration would be equal to the derivative of the velocity, or the second derivative of the position. So let's take a look at some examples. Particle's position is given by the function here, p of t. P of t is measured in centimeters, t is measured in seconds, and we're going to answer the following. Average acceleration, not velocity, acceleration on the interval, and give units. So we've got the position, e to the t times sine of t, and velocity is equal to p prime of t, which I do believe we found on the previous page, e of t times cosine of t plus e of t times sine of t, which we can clean up a little bit by factoring out e of t plus sine t. And I guess it doesn't really matter because we're going to be able to use the calculator for this to find the average acceleration. We're taking the average acceleration. We're going to use the velocity function for this. So the average acceleration is equal to the velocity at point 1 minus the velocity of 3 over 1 minus 3. All calculator work, and we'll get negative 10.403. And now units. This is estimating the average acceleration, thinking about second derivative essentially. So negative 10.403 centimeters per second squared. Centimeters per second squared. All right, so keeping it moving, we go and take a look at the next piece. The instantaneous acceleration, not the average, the instantaneous, and t is equal to 1.5. So just to refresh, we know position, we know velocity. Having this written in this form might help us to find acceleration, because acceleration, the instantaneous acceleration here, is equal to v prime of t, or p double prime of t. So we can find this. The acceleration is equal to v prime of t. And now here, we're going to take the derivative of this. Product rule. First times derivative of second, negative sine t plus cosine t plus second cosine of t plus sine t times derivative of the first. And that would be really, really, really horrible to solve, so we're not going to do that. We can do this in the calculator. So really you can go back in and plug this in and use the derivative function, or here, and we're going to be able to say that the acceleration at 1.5 seconds, which is the same thing as v prime at 1.5, is equal to 0.634 units, centimeters per second squared. Centimeters per second squared. Okay, let's take a look at a couple of more things here. This is a bit of a lengthy one, so I think I'm actually going to pause this so I can upload the video and then start again.